Hi all. So we're going to finish up our discussion on centripetal motion. And the focus on this tutorial, the last page, is simply the causes. The first two we're talking about centripetal acceleration, which are the effects or the effect that you feel when an object goes around a circle, whether it's a car on a road or you're in a satellite in orbit, anything. So the good news is this tutorial just centers around something we should be very familiar with, the second law of motion, F equals ma. We're going to focus on the F part, the net force, and then we're simply going to apply it to the ma part. And the only thing that's different than the last chapter is that how we calculate acceleration is using that v squared over r. So, here's a spoiler. Our central idea here is F, and I'm going to put a C here, equals m times AC. And the only difference between that and the previous one is the C represents centripetal motion. So we're going to focus on this, and we just got to be careful we don't make a silly mistake and think that centripetal force is a new type of force. It's just a generic way of saying forces that push something in a circle, but I'll explain that more later. Okay, so I already answered the first question. What caused an object to move in a circle and a curve in the first place? We never really talked about that much in the previous tutorials, but now we are. And of course, that's a net force. Okay, and that net force can be a variety of forces, and that's what we want to be able to understand. And if you don't have a net force acting on something, then the first law of motion kicks in, which means that objects would move in a straight line, or better put, at a constant velocity. Okay, so you don't have to draw this, but if I have something moving in a circle like this, there's got to be something pushing it inward. If you take away that force, let's say we take away the force right at the bottom, it just goes away, then the object must move in a straight line tangent to that point in the circle at that instant. So as long as there's a force, we'll continue moving in a curve, and so we just want to look at the nature of that force. Okay, so let me give you some situations here because we'll be doing mathematical examples later on. I'll show you in class, if I haven't done already, what if I twirl a can around in a string? Okay, so imagine, you don't have to draw this. Here's my can, here's a string, and it's going around and around in a vertical circle. Okay, so here's my hand that's twirling it around and around. And so if the can is moving in a circle, there's got to be something forcing it to continually change direction, if not its speed. Okay, so we would just say, all right, we know it's accelerating inward because that's what we learned about centripetal acceleration. Let's say we're at the top, okay? So something's got to be forcing it inward. So what would the force be? Well, there's actually two forces that's forcing it inward. There is gravity, and then there is tension in the string because of my hand pulling it inward. Now, if on the other hand, and again, I'm making it complicated, but I'm just going to go to the simpler situation. Imagine we're looking from above, and actually this is going to look like the same thing. We're looking from above, though, and the can is going in a horizontal direction, right? In this case, what's pulling it in is the tension in the string. So that's really what I want to get at, is in the case when you have a can on a string, always tension will be pulling it inward. Sometimes it'll be gravity, depending if it's a vertical circle. Okay, but I just want to, maybe I should stick with the horizontal part. Next one, roller coasters. So imagine we have a roller coaster that goes like this, and we can be at the bottom of the hill, or we can be at the top of the next hill as we're moving in a general direction this way. So what is the force that allows you to make this turn? Okay, well, we would just do a simple force diagram. This is nothing new. If I'm at the bottom of the hill, I've got a normal force pushing up, and I've got gravity pulling down, mg. Okay, but since the center of the circle is right here somewhere, right, because we're inside the circle here, that curve, then the force that really pushes you towards the center is the normal force, okay? Technically, well, actually, let me be more precise. It's the normal force minus the force of gravity, okay? We know that the normal force has to be bigger in this case because we're accelerating in towards the center, or in this particular case, up. Now, if we're at the top of the hill, we still have the same forces. We still have normal force, and we still have F of G, but the center of the circle is right here inside the circle here, the curve. So that means Fg has to be bigger because we're accelerating towards the center. So at the top of the hill, it just reverses. It's Fg minus Fn. And if you understand this, this will make your life a lot easier in the problems that we're going to solve. Okay, because what we can ask then is, what normal force do you feel at these cases? Because remember, it's a normal force is what you feel as your weight when you're in a roller coaster ride. And I believe we talked about this when we were talking about elevators. You're going to feel heavier here, and some of you may have experienced this, remember that, and you're going to feel lighter there. And it all can be calculated looking at it like that. So study that. Make sure you understand what I just did there, because it's really just the second law of motion. And the key understanding is the bigger force is the one that is towards the center of the circle. Okay, so let's say we're a car going around a curve on a road. Okay, so I'm going to draw a curve. We're looking from above. Here's the car. It's moving this way. We don't want it to slide off the road. We want to be able to turn. There's got to be something forcing it inward. So if you would draw a force diagram, we will know what force is forcing inward. Maybe it's less obvious, but it's really important that that's going to be static friction. So I'll put F of Fs. Okay, without friction, I think we know intuitively we're going to go in a straight line. We have no control. So it's the static friction. It's static because the car isn't sliding, it's not slipping as it goes through the curve. And then lastly, another form of circular motion is satellites around the Earth. So if there's the Earth and here's a satellite, right, what keeps the satellite going in a circle? Why doesn't it go off in a straight line? Tangent, something's got to be pulling it inward, and it should be pretty obvious that that's F of G. Okay, so what I want us to understand is the forces that cause something to move in a circle are different depending on the situation. But we can all lump them into the same category and call them a centripetal force. Okay, and centripetal forces, whoops, I already got forces there, is given a generic label F sub C. Now again, let me be very clear. If I ask you to draw a force diagram for something moving in a circle, you do not label anything F sub C. You label it normal force or gravity or static friction or tension depending on the situation. However, it's convenient to label the net force in a circle as a normal, as a FC, when we just go to do generic equations. Okay, and I'll try to explain that in a minute. Okay. So, with this idea of centripetal force, we have two ways of approaching centripetal motion. So I'm going to try to give you a conceptual construct to help you solve the problems. You don't have to use this. Okay, if you understand how to apply the second law, that's really all I'm going to teach you here. I'm just giving you a slightly different way of looking at it. Okay, so you can talk about a supply. In other words, depending on a situation, whether you're on a road or you're in an orbit or you're in a roller coaster, you're going to have a certain supply of force. That's simply the amount of gravity or normal force or tension, okay? And then you have a demand due to how fast you are traveling and how tight the curve is, the speed and the radius. And I should say, due to the speed, the radius, curvature, and the mass. Okay, let me be complete here. How much mass you're trying to turn. So those two can be related in the sense that supply, mathematically, can equal demand at the threshold of your ability to turn. Okay, so before I get into the mathematics of it, let me just give you a simple situation of a car going around a curve. If you're going, I think we know intuitively, if your car is going too fast, you will slide off the road. Or if the curve is really tight, in other words, it has a small radius, if you're going too fast, you will slide off the road. So why does that happen? Well, that happens because your demand is greater than your supply. Your demand depends on how fast you're moving, how tight the radius is, or the road is, and the mass you're moving, where the supply is the actual force that's there. How much gravity do you have? How much friction, etc. So generically, our supply is always going to be the centripetal force. And the centripetal force is the net force that is what we call radial. Radial means along the radius. Okay, so in the examples I did up here, these are all the supply forces. And then if we're going to just make it through the curve, then that supply is going to equal the demand. And the demand is nothing more than the application of the second law, the mass of the object multiplied by its centripetal acceleration. And the centripetal acceleration is v squared over r, so the demand side simply becomes mv squared over r. Okay? So in short, almost all the problems I'm going to ask you, it's basically going to be F net centripetal equals mv squared over r. Okay? Or the alternative way of doing that, and that all depends on your preference, is often that F net is just called the centripetal force. Let me again repeat myself. Centripetal force is not a new force. It's just a generic statement or a way of categorizing the force that pushes something in a circle. So let me do a quick example before we do more practice class. So let's say I've got a car of a certain mass. It's going a certain speed over a certain curve. And we have a force of friction of 4,800 based on the coefficient of friction and the normal force. Will the driver have to slow down in order to make this not to skid off the track? I should say off. Well, the approach we can do, I'm going to do it in steps, but you can do it at once, is look at my supply versus my demand. So what's my supply force? Well, the actual force is friction. If I want to be more complete, static friction. So I don't have to calculate it because you're told that it's 4,800 newtons. Okay. Now, I've got that much force based on the coefficient and the mass of the car, the normal force. Now, what's the demand? What am I asking for based on how fast I'm going? Well, I always calculate the demand as MAC, or better yet, MV squared over R. Okay, because AC, remember, is V squared over R. So, I put in the numbers, 600 kilograms, 50 squared, and divided by 120. Okay, I punch those numbers out in my calculator, and I get 12,500. Okay, so that's telling me I need 12,500 newtons of force to get through the curve at that speed. I only have 4,800, so do I need to slow down? Oh yeah. Okay, so then that leads to the next question. Well, then what is the maximum speed I can go for that amount of force? It's clearly got to be less than 50 meters per second. So how I'd approach that is simply do this. Take my demand force, in this case force of static friction, and set it equal to, my supply force, and set it equal to the demand. And again, the demand equation is always going to be that. Always. And that's nothing more than the second law of motion, F equals ma. Okay, so I now put in the numbers. I know that the supply force is still 4,800 newtons. That hasn't changed. I know that the mass of the car is 600. I'm looking for the maximum speed squared divided by R. R is still given. Okay, you can do the algebra, and if I solve for, well, let me just put in 120, and if I do the algebra, I see that the V maximum is 31 meters per second. You should work that out for yourself. So that's a very useful application. That's the fastest I can go on that track. Usually you want to go slower because you don't want to push it at the very extreme. So the last question, and this is important, would reducing the mass of the car make it easier going around a curve? We know we'd have to slow down, but would it be helpful if we had less people in the car, etc.? The quick answer to that is no, it would not be easier. And here's the reason why. Again, second law of motion. My supply force is friction static equals the demand on the force. So how do I calculate? You were told it was 4,800 newtons in this problem, but how would you calculate in general? Well, that would be mu static times the normal force. And usually in this case, the normal force is going to be the mass of the mg. Not always. If we had spoilers in that, then we could have additional things. But anyway, so if I just have normal force due to the weight of the car and the passage in the car, it becomes that equals mv squared over r, and we see that the masses cancel. So the maximum speed, v, doesn't depend on mass. So one way we could look at that conceptually is, even though you have more inertia you're trying to turn, you also have more force that allows you to turn. Okay, so we will do many more problems with this, and in the lab, look this over carefully, come into class with questions on what confuses you.